Some stars shine steadily while others pulse, flicker, or suddenly erupt in brightness. These are variable stars, cosmic beacons that reveal secrets about the universe. Today we'll explore how and why they change their light. If you enjoy this journey, please like, subscribe, share, and leave a comment with your favorite type of star. Thank you for watching. Now let's begin. A variable star is a star whose brightness changes as seen from Earth. The change may be large or small, regular or irregular, but it is enough that the light of the star does not remain steady. To the eye, most stars appear constant twinkling, only because of the unsteady atmosphere above. Yet over days, weeks, or even minutes, some stars genuinely rise and fall in their output of light. This shifting light is not an illusion, but a sign of processes inside or around the star. When astronomers speak of a variable star, they mean a star that shows measurable variation in its apparent brightness over time. To begin to understand this subject, it is useful to consider how starlight is measured and why changes are meaningful. The brightness of a star as seen in the sky is called its apparent magnitude. This measure is historical, dating back to ancient classifications, but in modern terms it is a logarithmic scale that compares flux, the amount of light reaching a telescope. When a star is constant, its magnitude stays fixed. When it varies, its magnitude increases or decreases in recognizable ways. To visualize such behavior, astronomers record brightness over many nights and plot the points on a graph. The horizontal axis shows time, the vertical axis shows brightness or magnitude, and the result is a curve. Such curves reveal patterns that can be slow, sharp, regular, or erratic. They are called light curves, and they serve as the fingerprint of the star's variability. The human eye can detect only the most striking changes. A mirror variable may fade until it is barely visible, and then return over hundreds of days to brightness that rivals a prominent star. But most variations are subtle and require careful measurement. Modern detectors, such as charge-coupled devices placed at the focus of telescopes, can measure changes of just 1 part in 100 or even smaller. This sensitivity allows astronomers to track stars that pulse by only a fraction of a magnitude, or that show small dips caused by an orbiting companion. The study of variable stars is therefore both ancient, with roots in visual discoveries like mirror in the 17th century, and modern, with precise electronic measurements carried out in space observatories. The first impression of a variable star is simply that it is not steady. Yet this simple fact opens a deep path into astrophysics. Light is the messenger that carries information from the star's surface to observers. When that light changes, something physical must be happening. The cause may be the star itself through pulsation or flares. The cause may be the geometry of an orbit when one star hides another from view. The cause may be interaction, when matter flows between close companions. Each pathway leads to a different family of variables, each with its own physical explanation and characteristic light curve. Thus, variability is not a single phenomenon, but a category of behaviors. Consider the timescales. Some stars change in minutes, producing rapid bursts of light. Others vary over hours or days with smooth cycles. Some take years or even centuries to complete a sequence. The amplitude of variation also differs. A Cepheid pulsates with a steady rise and fall of perhaps 1 magnitude. An R Lyrae shifts by a few tenths. A flare star may leap by several magnitudes within an hour. Eclipsing binaries can dip deeply when one star blocks another, then return to full brightness. These variations are not random but follow physical laws. They reflect mass, radius, temperature, chemical makeup, and internal processes of the star. To the scientist, variable stars are laboratories. Unlike a static star that shows only a constant output, a variable star reveals its inner structure by changing. By timing the cycle, measuring the amplitude, and comparing the color, astronomers deduce the density size and evolutionary state of the star. Periods and amplitudes are linked to physical properties. For Cepheids, the longer the period, the more luminous the star. This period-luminosity relation became one of the cornerstones of cosmic distance measurement. For RR Lyrae stars, the uniformity of their brightness allows them to serve as traces of galactic structure. The light curve is not just a curve, but a coded message about the star's identity. When describing variable stars, it is important to keep in mind the distinction between intrinsic and extrinsic variability. Intrinsic variables change because of processes within the star itself. Pulsations expand and contract the outer layers. Instabilities in nuclear burning or magnetic fields can alter the output. Extrinsic variables change because something outside the star modulates the light. An eclipsing binary dims because a companion moves in front. A rotating star with dark spots shows small dips as the spots rotate into view. Both forms are valuable and both are studied with equal care. The classification of variable stars rests on this division. Historically, variable stars were once puzzling exceptions. The constancy of the heavens was assumed, so a star that appeared and disappeared challenged that assumption. Mira, first noted in the late 16th century, was given its name, meaning wonderful, because of its remarkable behaviour. Over time, hundreds of others were catalogued. Today, millions are known thanks to wide surveys such as those by space missions. Rather than exceptions, they are a significant part of stellar populations. Every class of star, from small dwarfs to massive giants, can show variability in some form. For observers, the attraction lies in their richness. Amateur astronomers can still contribute by monitoring stars night after night, adding to databases maintained by international organizations. Professional observatories, including space telescopes, provide high-precision light curves and spectra. Together, these data sets feed into models of stellar interiors and galactic structures. Thus, variable stars bridge individual curiosity and professional science. In calm reflection, one sees that the changing brightness of stars is not a distraction but a signal. It is the star communicating aspects of its inner life. A stable star shows little of itself. A variable star opens a window into motion, interaction, and instability. To follow the quiet rise and fall of its light is to listen to the rhythms of stellar physics. The variations may be tiny, but they are steady and meaningful. The sky is full of such signals, waiting patiently to be measured, understood, and connected to the deeper story of stellar evolution. A light curve is the essential tool for studying variable stars. It is a graph that shows how the brightness of a star changes with time. On the horizontal axis is time often measured in hours, days, or years, depending on the phenomenon. On the vertical axis is brightness measured in magnitudes or in flux units. Each observation of the star is placed on the graph, and together these points form a curve that tells the story of the variation. For a constant star, the line would be flat, showing no change. For a variable star, the line rises and falls, sometimes smoothly, sometimes sharply. Light curves become the fingerprints of stars, each with a unique shape that reveals the mechanism behind the change. The shape of the light curve is as important as the fact of variation. For a Cepheid star, the curve shows a gradual rise in brightness, followed by a slower decline, repeating with remarkable regularity. For an RR Lyrae star, the rise is steep and the fall more gradual, giving a characteristic asymmetric sawtooth form. For an eclipsing binary, the light curve shows deep dips at regular intervals, as one star passes in front of the other, with smaller secondary dips when the second star is hidden. For a flare star, the curve shows a sudden spike followed by a quick decline. These shapes are not random but result from real physical processes in or around the star. By reading the curve, astronomers learn what is happening. The amplitude of the light curve, or the amount by which brightness changes, is also significant. Some stars change by several magnitudes, meaning they brighten or fade by large factors. Others vary by only a few hundredths of a magnitude. Sensitive instruments can record even these small changes. Amplitude often relates to the physical scale of the process. Pulsating giants may have large swings because their outer layers expand and contract significantly. Stars with surface spots show only small variations because the spots cover limited areas. In eclipsing systems, the depth of the dip depends on the relative sizes and brightnesses of the stars. Another key property is the time it takes for the brightness pattern to repeat. Periods can be measured with high accuracy from light curves. Cepheid variables have periods of a few days to a few months. RR-Lyrae stars have periods less than 1 day. Mira variables have periods of several hundred days. Eclipsing binaries repeat their dips according to their orbital periods, which may range from hours to years. The precision with which periods can be measured makes variable stars excellent clocks. Some stars keep their rhythm so consistently that small changes in period signal slow evolution or the presence of additional companions. The color of the star can be studied together with its light curve. Stars emit light across a range of wavelengths, and the balance between blue and red light indicates surface temperature. As a star pulsates, its temperature may rise and fall, shifting its color index. Measuring brightness in different filters allows astronomers to trace both light and color changes. This adds another dimension to the curve, showing not just how bright the star is, but how its energy distribution shifts. For pulsating variables, this behavior matches the expansion and contraction of their envelopes, giving insight into their physical structure. Spectroscopy deepens the picture further. By spreading light into its component wavelengths, astronomers see absorption lines that shift as the star moves or as layers expand and contract. When matched with light curves, spectral changes reveal velocities, densities, and chemical abundances. For example, in Cepheids, the spectral lines move back and forth in step with the light variation, confirming the pulsation of the outer layers. In eclipsing binaries, spectral lines from each star shift due to orbital motion, allowing measurement of their masses. Light curves and spectra together give a full account of the dynamics. To gather light curves requires patience and repetition. A single night of data is rarely enough. Cycles must be followed through many repetitions to reveal their pattern. For centuries, amateur observers contributed by recording visual estimates with the naked eye or small telescopes. They compared variable stars with nearby stars of known brightness, estimating changes night after night. These estimates, though rough, built up long-term records of cycles. Today, electronic detectors provide precise data, but the principle remains the same. Steady monitoring builds the curve. Space missions have advanced the field dramatically. Observatories above Earth's atmosphere avoid the interruptions of clouds' day-night cycles and atmospheric distortions. Missions such as the Kepler telescope recorded brightness of hundreds of thousands of stars continuously for years, producing light curves of exquisite detail. These data revealed not only known variables but also countless new types and subtle variations. Stars that seemed constant from the ground were found to flicker or pulse when observed with space-based precision. The study of variable stars has therefore expanded from a catalogue of unusual cases to a vast exploration of stellar behavior. Patterns in light curves allow classification. Astronomers organize variable stars by their curves, separating pulsators, eclipses, eruptive stars, and others. Subclasses are defined by period range, amplitude, and curve shape. Each class points to a mechanism, Cepheids and RR Lyrae belong to pulsators. Algol systems belong to eclipsing binaries. Dwarf novae belong to cataclysmic variables. The classification is practical, helping astronomers interpret data quickly, but it also reflects underlying physics. In many cases, seeing the curve is enough to suggest the type of star and its role in stellar evolution. Yet light curves also reveal complexities. Some stars do not follow simple cycles. Their amplitudes change over time or their periods drift. Some pulsators show multiple overlapping modes producing beat patterns in the curve. Some eclipsing binaries show irregularities caused by mass transfer or by third companions disturbing the orbit. These features remind astronomers that stars are not machines but evolving bodies with changing conditions. Each deviation from simplicity is itself a clue. In quiet reflection, one can think of light curves as the voices of stars. They are not static pictures, but records of change line after line tracing the rhythm of stellar lives. The curves do not rush but move at their own pace, some slow, some quick, each steady and true. They show the measured breathing of stars, the eclipses of companions, the flares of magnetic fields, and the growth of instabilities. To look at a light curve is to follow the patient heartbeat of a distant sun. The science rests on careful data, but the impression is one of calm continuity. On the Hertzsprung-Russell diagram, which is a plot of stellar brightness against temperature, there lies a region known as the instability strip. This band runs diagonally across the diagram, cutting through areas where stars evolve during different stages of their lives. Stars that cross into this strip often become variable, because conditions in their outer layers allow pulsations to grow instead of fading away. The instability strip is not visible in the sky, but it is visible in the diagram that astronomers use to classify stars. It is a quiet pathway where stellar stability gives way to rhythmic change. To understand why this happens, it helps to think about the balance between gravity and pressure in a star. A star holds itself up because the inward pull of gravity is matched by the outward push of gas pressure created by nuclear burning in its core. In most regions of the diagram, this balance produces a stable star that shines with steady light. In the instability strip, however, the balance becomes delicate. Certain layers in the star absorb and release energy in a way that drives pulsation. This process is called the opacity mechanism, or the Kappa mechanism, because it depends on how opaque the gas is to radiation. In these stars, helium plays an important role. When helium is partially ionized, meaning some of its electrons are stripped away, the gas can trap heat as it becomes more opaque. As a layer of helium absorbs radiation, it heats up and expands. When it expands, it becomes less opaque, letting radiation escape. That cooling allows the layer to contract again. This cycle repeats, and with each cycle, energy is added to the oscillation. The result is that the outer layers of the star begin to move in and out, driving changes in radius, surface temperature, and brightness. This is why stars in the instability strip pulsate with regular periods. The strip is defined by temperature and luminosity. On the hot side, stars are stable because their envelopes are fully ionized and do not trap heat effectively. On the cool side, stars are also stable because their envelopes recombine and lose the ability to drive pulsations. In between, in the strip, conditions are just right for the Kappa mechanism to operate. The exact edges depend on metallicity, the abundance of elements heavier than helium, and on mass. More massive stars cross higher in the strip and become Cepheids. Less massive stars cross lower and become RR Lyrae or Delta Scuti stars. The importance of the instability strip is that it explains why certain types of variables exist where they do. Cepheids, for instance, are found in the strip for intermediate to high luminosity. RR Lyrae occupy a narrow horizontal region for older low-mass stars. Delta Scuti stars appear at the lower end among main sequence or slightly evolved stars. The strip organizes what might seem like a confusing diversity into a single framework. By locating a star on the Hertzsprung-Russell diagram, astronomers can predict whether it is likely to show pulsations. Observations confirm this picture. When star clusters are plotted on the diagram, variables appear concentrated along the strip. In globular clusters, RR Lyrae stars line up in the strip where old stars of about half the mass of the Sun have evolved off the main sequence. In younger open clusters, delta Scuti stars are found near the lower end. Supergiant Cepheids are visible in galaxies where massive stars have crossed the strip during later evolutionary stages. The universality of the strip across clusters and galaxies shows that the mechanism is not an accident, but a fundamental outcome of stellar physics. The periods of stars in the strip reflect their density. For pulsations, the period is roughly proportional to the square root of the average density of the star. Large luminous Cepheids are less dense, and thus have longer periods measured in days or weeks. Smaller, denser RR Lyrae stars have shorter periods measured in hours. This relation gives another way to link the diagram to physical properties. When astronomers measure a period from a light curve, they can infer where the star lies on the diagram and what its internal structure must be. Although the instability strip gives a clear framework, not all variables fit neatly within it. Some stars outside the strip pulsate because of other mechanisms such as strange modes in hot massive stars or convective driving in cool stars. Others vary because of external causes like eclipses or flares. Still, the strip remains a central concept because it explains the most regular and predictable pulsators. It acts as a reminder that even in the apparent scatter of stellar evolution, certain paths produce reliable outcomes. Astronomers have refined the borders of the strip through both observation and theory. Space missions that record light curves of thousands of stars allow precise placement of variables on the diagram. Theoretical models calculate how ionization zones behave in stellar envelopes and where driving should occur. Together, these approaches match well, though small discrepancies remain. For example, metallicity shifts the position of the strip so stars in metal-poor galaxies may pulsate in slightly different regions. These details are important for using variables as distance indicators, since the relation between period and luminosity can depend subtly on chemical composition. The strip also shows the connection between stellar evolution and variability. Stars do not remain fixed on the diagram. As they exhaust hydrogen in their cores and burn heavier elements, they move across the diagram. Many stars cross the instability strip more than once in their lifetimes. Each crossing can ignite pulsations. Thus, a Cepheid may have once been a stable main sequence star, but during its journey across the diagram it entered the strip and began to pulsate. Variable stars then are not separate species, but ordinary stars passing through a particular phase. In reflection, the instability strip is a quiet boundary in the vast diagram of stellar life. It is not a visible line in the sky, but a region in theoretical space where stars reveal themselves by their changes. The strip connects brightness, temperature, structure, and time into a single pathway. Stars enter it and become variable, then leave it and become steady again. By tracing this strip, astronomers see how the rhythms of stellar pulsation emerge from the deeper balance of matter and energy. The concept is simple, yet profound. In certain conditions, stars cannot remain constant, but must move in and out like a breath, leaving their signature on the light that reaches across space. Among the stars that lie within the instability strip, Cepheid variables stand out as some of the most important and best studied. They are luminous, massive stars that pulsate with regularity, producing light curves that repeat with a predictable pattern. Their cycles are not random flickers, but steady rhythms that can last for days or weeks, each repetition almost identical to the last. To the observer, a Cepheid brightens quickly, then fades more gradually in a repeating heartbeat of light. This characteristic curve is the hallmark of Cepheids and has been measured in countless galaxies across the universe. The mechanism that drives Cepheid pulsation is the kappa mechanism, the same opacity effect described in connection with the instability strip. In Cepheids, it occurs primarily in a layer where helium is partially ionized. When the star's outer layers are compressed, the opacity increases and radiation becomes trapped, heating the gas. This trapped energy causes the layer to expand outward. As it expands, the opacity drops, radiation escapes, and the gas cools, allowing the layer to contract again. This cycle reinforces itself, sustaining regular pulsations. Each expansion and contraction alters the star's radius, surface temperature, and luminosity, leading to the observed changes in brightness. Cepheids are divided into two main groups, classical Cepheids and type II Cepheids. Classical Cepheids are young, massive stars several times more massive than the Sun, often found in the spiral arms of galaxies. They are relatively metal-rich and have periods ranging from about 1 to 50 days. Type II Cepheids are older, lower-mass stars often found in globular clusters in the halo of galaxies. Their periods are generally shorter, and they are less luminous at a given period than classical Cepheids. Despite these differences, both types pulsate in the same fundamental way, and both follow relations between their period and luminosity. The period-luminosity relation is the most celebrated property of Cepheids. In the early 20th century, astronomer Henrietta Swan Leavitt discovered that in the Small Magellanic Cloud, brighter Cepheids had longer periods. Because the stars in that galaxy were all roughly the same distance away, their apparent brightness differences must have been intrinsic. This finding provided a direct link. By measuring the period of a Cepheid, one could infer its luminosity, and from that its distance. This relation transformed Cepheids into standard candles tools for measuring distances far beyond the reach of parallax methods. The usefulness of Cepheids rests on the precision of this relation. Modern calibrations using data from the Hubble Space Telescope and Gaia mission tie the period-luminosity relation to accurate distances within our galaxy. Once calibrated, the relation can be applied to Cepheids in nearby galaxies. By measuring their periods and apparent magnitudes, astronomers calculate distances across millions of light-years. This method was crucial for Edwin Hubble's discovery that galaxies lie far beyond the Milky Way, and that the universe itself is expanding. Cepheids were therefore central in reshaping cosmology, providing the first reliable rung of the extragalactic distance ladder. The light curves of Cepheids are not identical, but vary in shape with period. Short-period Cepheids show relatively simple curves, while long-period ones may display secondary bumps or humps. These differences arise from interactions between pulsation modes within the star. Detailed studies of the curves allow astronomers to refine models of stellar interiors, since the exact timing of the rise-fall and secondary features depends on how energy moves through the star's layers. Thus, Cepheids not only serve as distance indicators, but also as test beds for theories of stellar structure. Spectroscopic observations add further depth. As a Cepheid pulsates, its spectral lines shift due to the motion of its surface. These shifts confirm that the star's outer layers move in and out with each cycle. By combining velocity data with brightness changes, astronomers measure the star's radius variation, and through methods such as the Baeyer-Wesselink technique obtain absolute sizes and luminosities. Such independent checks strengthen the reliability of Cepheids as cosmic yardsticks. They also reveal subtle effects such as shock waves that travel through the atmosphere during pulsation, producing brief features in the spectrum. Despite their regularity, Cepheids do show complexities. Some have amplitudes or periods that change slowly over time, reflecting gradual evolution. A star moving through the instability strip may change its pulsation characteristics as it shifts in temperature and density. Others show additional modes of oscillation leading to small irregularities. These deviations are not flaws but clues to how real stars differ from ideal models. They remind astronomers that variability arises in living systems, not mechanical oscillators. Each observed difference refines understanding of stellar physics. The environments of Cepheids also matter. Interstellar dust can dim and redden, their light altering apparent brightness and colour. Correcting for these effects requires observations in multiple wavelengths from optical to infrared. Modern surveys often rely on infrared measurements where dust effects are smaller and the period-luminosity relation is tighter. This improves accuracy when Cepheids are used to measure distances to galaxies with significant dust. The refinement of such corrections is one reason Cepheids remain vital in cosmology, even with newer distance indicators. Cepheids also connect to the larger framework of galactic structure. Because they are luminous, they can be seen across the Milky Way, tracing spiral arms and mapping the distribution of young, massive stars. In nearby galaxies, Cepheid populations reveal star formation patterns and histories. They are thus not only distance markers, but also traces of stellar populations and galactic evolution. Their presence marks regions of recent star formation, linking the physics of pulsation to the larger story of how galaxies grow and change. In reflection, Cepheid variables are both simple and profound. Their steady light curves and clear relations make them predictable. Yet the reason they pulsate lies in delicate balances of opacity, density and energy transport. Their usefulness to astronomy arises because nature has given them regular rhythms that can be measured across space. To watch a Cepheid brighten and fade is to witness a vast star breathing in and out, but to measure its period is to unlock distances on a cosmic scale. Cepheids thus stand as quiet markers, bridging the behavior of individual stars with the shape of the universe itself. While Cepheids are the most famous pulsating variables, there are other classes that are smaller and less luminous but equally important. Among these are the RR Lyrae stars and the Delta Scuti stars. Together they show that pulsation is not limited to massive supergiants, but also occurs in lower mass stars at different stages of their evolution. These classes provide tools for studying old populations and for exploring the fine details of stellar interiors. Their light curves may be less grand than those of Cepheids, but their scientific value is just as enduring. RR Lyrae stars are low-mass old stars that have evolved off the main sequence and are burning helium in their cores. They are found in abundance in globular clusters and in the halos of galaxies, making them valuable traces of ancient stellar populations. Their periods are short, typically less than 1 day, and their amplitudes are moderate, often about half a magnitude to a full magnitude. The shape of their light curves resembles a steep rise in brightness, followed by a slower decline, producing a sawtooth pattern. This distinct shape allows them to be identified easily in surveys. The importance of RR Lyrae stars lies in their near-uniform luminosity. While they are not as luminous as Cepheids, they all have roughly the same absolute brightness, particularly in the visual band. This makes them standard candles on a smaller scale. By measuring their apparent brightness, astronomers can determine distances to globular clusters and nearby galaxies. Although the reach of RR Lyrae is limited to hundreds of thousands of light-years, their abundance and consistency make them invaluable for mapping the structure of the Milky Way and for measuring distances within the local group of galaxies. In globular clusters, RR Lyrae stars line up neatly on the Hertzsprung-Russell diagram, crossing the instability strip where old low-mass stars pulsate. Their presence confirms both the physics of the instability strip and the ages of the clusters. By counting and classifying RR Lyrae stars, astronomers can also infer metallicity, since the exact properties of their light curves depend on chemical composition. Metal-poor clusters tend to show RR Lyrae with different characteristics than metal-rich clusters, reflecting how internal structure changes with composition. Thus, R Lyrae are not only distance markers, but also probes of stellar populations. Some RR Lyrae stars show additional effects such as the Blaschko effect, a modulation of amplitude and phase over longer timescales. This phenomenon has been studied for more than a century, but is still not fully understood. It may involve interactions between pulsation modes or magnetic fields. The presence of such modulations illustrates that even stars with seemingly simple rhythms can display complexity upon closer inspection. Long-term monitoring is required to trace these changes and to refine models of pulsation. Delta Scuti stars form another important group of pulsators. They are typically stars of intermediate mass, about 1.5 to 2.5 times the mass of the Sun, located near the main sequence or just beyond it. Their periods are very short, ranging from about half an hour to a few hours. Their amplitudes are usually small, often only a few hundredths of a magnitude, though some show larger variations. Because their changes are so rapid and subtle, they require precise and continuous observations to detect and analyze. The variability of Delta Scuti stars arises from the same Kappa mechanism acting in ionization zones within their envelopes, but their relatively small size and high density lead to short periods. Many Delta Scuti stars pulsate not only in one mode but in several simultaneously. This produces complex light curves with overlapping frequencies, creating beat patterns and irregular appearances. With modern space missions that record brightness with extreme precision, hundreds of frequencies have been detected in individual Delta Scuti stars. These stars therefore serve as natural laboratories for astroseismology, the study of stellar oscillations as probes of internal structure. By analyzing the multiple pulsation modes of Delta Scuti stars, astronomers can infer details about density, rotation, and composition. The frequencies depend on conditions deep inside the star, so the star effectively reveals its interior through its vibrations. This method is similar in principle to seismology on Earth, where waves from earthquakes reveal the structure of the planet. Astroseismology has become a powerful field, and Delta Scuti stars are central to it. Even though their light curves may appear irregular at first glance, careful analysis shows they contain a wealth of information. Both RR Lyrae and Delta Scuti stars demonstrate the diversity of pulsation in the instability strip. RR Lyrae are old and uniform, marking ancient populations and providing distance measures. Delta Scuti are younger and more complex, revealing interiors through multiple modes. Together they show that variability is not a rare curiosity, but a common stage of stellar evolution. They remind us that stars across a wide range of masses and ages can become unstable under the right conditions, each revealing its nature through subtle or dramatic changes in light. Observations of these stars continue to refine theories. Long-term monitoring of RR Lyrae reveals slow period changes as stars evolve, consistent with predictions of stellar evolution. High-precision data from missions such as Kepler and TS reveal new details about Delta Scuti oscillations, challenging models to match observed frequencies. Each advance shows that even familiar classes of variables still hold surprises. The study of these stars is not complete but ongoing, with each dataset adding clarity and raising new questions. In quiet reflection, RR Lyrae and Delta Scuti stars embody two sides of stellar variability. One side is steady and uniform, giving simple and reliable measures of distance and age. The other is intricate and layered, offering complex oscillations that carry hidden information about stellar interiors. Both types pulse in silence far beyond Earth, their rhythms repeating endlessly. Observers follow them patiently, noting each rise and fall of light, drawing from these cycles the lessons of stellar structure and history. They're not dramatic beacons, but modest stars whose quiet flickers guide understanding of the galaxy and the universe. Long-period pulsators form another important family of variable stars. These include mirror variables, semi-regular variables, and other giant stars that show cycles lasting hundreds of days. Their behavior is slower and more dramatic than the short-period pulsators, with brightness changes large enough to be seen with the unaided eye. These stars are typically red giants, or asymptotic giant branch stars near the final stages of their lives. Their extended outer layers and unstable interiors make them prone to large pulsations, driven by the same opacity mechanism but amplified by their immense size and low density. Mirror variables take their name from the star Mirror in the constellation Cetus, one of the first known variables. Mirror itself brightens over about 11 months from near invisibility to a star that rivals the brightest in the sky. This cycle repeats with remarkable regularity, though its amplitude and timing can shift slightly from one period to another. Mirror is a red giant several hundred times the radius of the Sun, with a cool surface temperature that gives it a reddish color. Its variability is caused by pulsation of its extended atmosphere, which expands and contracts in response to opacity changes in molecular layers. The brightness swings of mirror variables are often several magnitudes, making them striking even without instruments. Semi-regular variables are related to mirror stars but show less regularity. Their periods are still long, typically a few hundred days, but their amplitudes are smaller and their cycles less consistent. Some show multiple overlapping periods producing beats and irregular changes. Others vary in both amplitude and period from cycle to cycle. These stars occupy similar regions of the Hertzsprung-Russell diagram as mirror variables, but are at slightly different evolutionary stages or have different internal structures. Their variability reveals the complex dynamics of late stellar evolution, where convection, pulsation, and mass loss interact. The physics of long-period pulsators involves more than simple radial oscillation. Their extended envelopes are cool enough for molecules and dust to form. As the star expands, these molecules contribute to opacity changes, further driving pulsations. Dust can absorb and scatter light, altering the star's apparent brightness and color. In addition, pulsations help lift material from the star's surface, feeding stellar winds that carry mass into space. Thus, variability and mass loss are linked, and mirror stars are significant contributors to the enrichment of the interstellar medium with carbon, oxygen, and heavier elements. The light curves of long-period pulsators are broad and smooth, showing gradual rises and declines. For mirrors, the curve often shows an asymmetric shape, with a faster rise to maximum brightness and a slower decline. For semi-regulars, the curve may drift in amplitude or show secondary variations. Because the periods are so long, building complete light curves requires monitoring over many years. Historical records going back centuries provide valuable data showing how the stars have behaved over human lifetimes. Such long-term monitoring remains essential, as these stars can change on timescales that match or exceed centuries. Observations across multiple wavelengths reveal further details. In infrared light, mirror variables are often brighter than in visible light, because their cool atmospheres emit strongly in longer wavelengths. Infrared observations also penetrate dust that may obscure them in visible bands. This has made space-based infrared telescopes valuable for studying these stars. Spectroscopy shows strong molecular absorption features, confirming the complex chemistry of their atmospheres. Radial velocity measurements reveal the motion of their surfaces as they expand and contract, providing direct confirmation of pulsation. Mass loss is one of the defining features of long-period pulsators, The pulsations drive material outward, and radiation pressure on dust grains helps push this material away from the star. Over time, a Mira star can lose a significant fraction of its mass, creating a circumstellar envelope of gas and dust. Eventually, this process leads to the shedding of the outer layers and the formation of a planetary nebula, leaving behind a white dwarf. Thus, the variability of these stars is directly linked to their final evolutionary fate. Their changing brightness is a visible sign of processes that recycle stellar material into the galaxy. Theoretical models of long-period pulsators face challenges. The interactions between pulsation, convection, radiation, and mass loss are complex. Simulations attempt to reproduce the observed periods, amplitudes, and spectra, but uncertainties remain. Observations provide constraints. The relationship between period and luminosity, for instance, is well established for Mira variables. This relation allows them to be used as distance indicators, though with less precision than Cepheids or RR Lyrae stars. Still, they extend the range of variable stars useful for measuring cosmic scales, especially in infrared surveys of nearby galaxies. Semi-regular variables highlight the diversity within this group. Some may evolve into Mira stars, while others may fade in amplitude as they lose mass. Their irregularities may result from interactions between multiple pulsation modes or from changes in convection patterns in their deep envelopes. Monitoring large samples of semi-regular variables helps build statistical understanding even when individual stars show erratic behavior. Together with Miras, they form a continuum of variability among late-type giants. In reflection, long-period pulsators show the quiet but profound changes of aging stars. Their cycles are slow-lasting many months, and their light curves swing widely. To follow a Mira star is to follow a rhythm measured not in minutes or hours, but in seasons and years. Each cycle repeats, yet no two are exactly alike, and the star gradually changes as it loses mass and evolves. The variations are not sudden outbursts, but steady, patient pulsations, the breath of stars nearing the end of their lives. They teach that variability is not only the mark of youthful or intermediate stars, but also a sign of decline linking stellar lives to the enrichment of the cosmos. Pulsation in stars can occur in more than one way. In some cases, the entire star expands and contracts together with every layer moving in and out in unison. This is called radial pulsation, and it is the mode most often described when speaking of Cepheids, RR, Lyrae, and Mira variables. In other cases, only certain regions of the star's surface or interior oscillate, while others remain still or move differently. These are called non-radial pulsations. The distinction is important because it shows that pulsation is not always a simple breathing in and out, but can be a more intricate vibration with many overlapping patterns. In radial pulsation, the star's layers act like concentric shells. The pressure inside builds up and pushes the surface outward. As the star expands, it cools, the pressure drops, and gravity pulls it back in. The cycle repeats with a rhythm determined by the average density of the star. For Cepheids and RR Lyrae stars, this produces the steady periodic light curves that can be measured with great accuracy. The pulsation is essentially the star's whole body moving together in a predictable way, like a ball that expands and contracts in perfect symmetry. Non-radial pulsations are more complex. In these, some parts of the surface move outward while others move inward. The star develops patterns of motion similar to waves on a vibrating drum or ripples on a pond. These waves are described in terms of spherical harmonics, mathematical patterns that can wrap around a sphere in many ways. The number of nodes or points that remain still determines the complexity of the pattern. Some modes affect mainly the surface, while others probe deep into the interior. The star may pulsate simultaneously in several such modes, creating a tapestry of oscillations. Light curves from non-radial pulsators can look irregular or intricate since many frequencies may overlap. For some stars, the amplitudes of individual modes are small, only a few thousandths of a magnitude, but when recorded with sensitive instruments, the patterns become visible. The data often reveal dozens or even hundreds of distinct frequencies. Stars such as Delta Scuti and Beta Cepheid are prime examples where non-radial pulsations dominate. Their study requires long uninterrupted observations, often best achieved from space missions, that avoid the gaps and noise of ground-based monitoring. The physical cause of non-radial pulsations is still the same basic balance of pressure, gravity, and opacity, but the way oscillations propagate through the star allows for more diverse outcomes. Some modes are driven by the same Kappa mechanism that powers radial pulsations. Others may be influenced by convective motions or by interactions between radiation and matter in specific zones. In hot stars, iron ionization zones can trigger pulsations. In cooler stars, convection may play a role. The precise combination of conditions decides which modes are excited and which remain damped. Astroseismology, the study of stellar oscillations, has grown from this realization. By analyzing the frequencies of non-radial modes, astronomers can infer the internal structure of stars with remarkable detail. Just as seismology on Earth reveals the structure of the planet through the study of earthquakes, stellar oscillations reveal densities, rotation rates, and internal layering. For example, observations of non-radial modes can show whether a star's core is rotating faster than its surface, or how chemical composition varies with depth. Each frequency acts as a probe of a different part of the stellar interior. Radial pulsations, though simpler, also reveal much. Their periods scale with density, so measuring them constrains size and mass. When combined with luminosity and temperature, they provide strong tests of models of stellar evolution. Non-radial pulsations with their multitude of frequencies go further, allowing astronomers to build a three-dimensional picture of stellar interiors. Together, radial and non-radial pulsations form a spectrum of behavior that enriches the study of variable stars. An example of how this plays out can be seen in the Delta Scuti stars. Many of them exhibit both radial and non-radial modes simultaneously. The resulting light curves are complex, but frequency analysis separates the contributions. Space telescopes such as Kepler have revealed hundreds of distinct modes in individual stars, far more than ground-based observations had detected. These data provide detailed checks on theoretical models, pushing refinements in understanding of convection, opacity, and energy transport. Another example is the Beta Cepheid star's hot and massive objects that show short-period pulsations driven by opacity in iron ionization zones. Their non-radial oscillations reveal conditions in the deep interiors of high-mass stars where nuclear burning and rotation shape evolution. The study of these pulsations helps constrain models of how massive stars evolve, lose mass, and eventually end their lives in supernovae. Without the clues from pulsation, much of this internal physics would remain hidden. Radial and non-radial modes can also coexist in different layers. Some modes called P modes or pressure modes are driven by pressure forces and have higher frequencies. Others called G modes or gravity modes are driven by buoyancy and have lower frequencies. Pressure modes sample the outer layers while gravity modes penetrate the deep interior. Hybrid pulsators show both kinds, providing especially powerful constraints. By measuring both P modes and G modes, in the same star, astronomers can connect surface conditions with core processes. Theoretical modeling of pulsation requires solving complex equations of stellar structure and oscillation. Predictions of which modes should be excited depend on opacities, convection treatments, and rotation rates. Observational data from variable stars test these models and reveal where refinements are needed. For example, Discrepancies between predicted and observed frequencies have led to adjustments in opacity tables and convection physics. In this way, variability drives improvements in the broader field of astrophysics. In quiet reflection, the distinction between radial and non-radial pulsations highlights the diversity of ways stars can vary. Some stars move in simple symmetric rhythms, expanding and contracting, like a single organism breathing steadily. Others vibrate with multiple overlapping modes, their surfaces alive with intricate patterns of motion. Both forms remind us that stars are not rigid bodies but fluid spheres of gas and plasma, responsive to small changes in pressure, temperature, and opacity. Their variations are steady, slow and predictable when viewed with patience, and in those variations lies the key to their hidden interiors. Not all variable stars owe their changes in brightness to pulsations. Some vary because they rotate. As a star spins, features on its surface move into and out of view, producing small changes in brightness that repeat with the rotation period. The most common cause of such rotational variability is the presence of star spots regions on the surface that are cooler and darker than the surroundings due to intense magnetic activity. These spots are similar in principle to sunspots on the Sun, though in some stars they can be much larger and cover a greater fraction of the surface. As the star turns, the spots alter the total light that escapes toward the observer, creating a light curve that rises and falls with each rotation. Rotation periods vary widely between stars. A massive young star may rotate in less than a day, while a giant may take months. The light curves of rotating spotted stars reflect this diversity. Some curves show smooth sinusoidal patterns with brightness dipping once per rotation. Others show more irregular features if multiple spots of different sizes and positions exist. In stars with strong magnetic activity, spots can appear, grow and fade, so the pattern of variability evolves over time. The amplitude of brightness change is usually small, often only a few hundredths of a magnitude, but sensitive instruments can detect these subtle signals. The Sun provides the closest example. Sunspots rotate across the solar disk, producing small changes in solar brightness. While the effect is slight, it demonstrates the principle. In younger and more active stars, the magnetic fields are stronger and spots more extensive. These stars show more pronounced rotational modulation, making their light curves more dramatic. For astronomers, these variations give information about stellar rotation, magnetic cycles, and surface activity. They allow rotation rates to be measured even when spectral line broadening is insufficient to provide a clear answer. Magnetic activity is tied to the internal structure of a star. Stars with convective outer layers generate magnetic fields through dynamo processes in which motion of conducting plasma creates and amplifies magnetic fields. The strength of the dynamo depends on rotation. Faster rotating stars tend to have stronger fields and more active surfaces. This is why young stars which rotate rapidly often display strong spot activity and variability. As stars age, they lose angular momentum through stellar winds, their rotation slows, and their activity decreases. The gradual change in variability with age provides a way to study stellar evolution. Some stars show more extreme versions of this behavior. AP and BP stars, which are chemically peculiar stars with strong magnetic fields, often display rotational variability. In these stars, surface regions enriched with certain elements cause bright or dark patches. As the star rotates, these patches change the integrated light, producing periodic variability. The periods reflect the rotation rates, which are often longer than those of similar non-magnetic stars. The study of these variations reveals both the rotation and the distribution of surface features shaped by magnetic fields. Rotational variability is not always limited to spots. In some cases, bright regions contribute instead of dark ones. Hot stars with magnetic fields can trap plasma in their magnetospheres, creating bright spots or clouds that co-rotate with the star. As these structures pass in and out of view, they alter the light curve. Thus, both dark spots and bright regions can modulate brightness depending on the physical processes at work. The common theme is that the star's rotation brings asymmetries into and out of sight. Space missions have provided a wealth of data on rotational variables. Continuous monitoring of thousands of stars by satellites such as Kepler and TESS has revealed rotational modulation across a wide range of stellar types. In many cases, light curves show spot patterns drifting over time, reflecting differential rotation, where different latitudes rotate at different rates. For example, the Sun rotates faster at the equator than at the poles, and similar effects are seen in other stars. By analysing these patterns, astronomers learn about internal rotation and magnetic activity cycles. Rotation also links variability to stellar age through a method known as gyrochronology. Since stars spin down as they age, measuring their rotation period provides an estimate of their age. Variability due to spots becomes the key observable for this method. By studying populations of stars with known ages, astronomers calibrate the relation between rotation and age. Though there are uncertainties and scatter, the principle offers a way to date stars far beyond the solar system. Rotational variability thus contributes to both stellar physics and galactic archaeology. In addition, rotation affects pulsation. In some stars, rotation modifies pulsation frequencies, splitting or shifting them. Thus, rotational variables and pulsating variables are not always distinct categories. A star may pulsate while also showing rotational modulation, and disentangling the two requires careful analysis. The interplay between rotation and pulsation provides further information since it connects surface features to internal structure. This shows that variability is often a combination of mechanisms, not a single cause. Rotational variability is generally gentle and repetitive, lacking the dramatic swings of long-period pulsators or the sudden flares of eruptive stars. It is quiet, steady modulation like a slow wheel turning. Observers track the dips and rises in brightness and deduce the star's spin, its surface features, and its activity level. Over months or years, the patterns evolve, tracing magnetic cycles that wax and wane. These changes remind us that stars are not perfectly smooth spheres, but dynamic surfaces with magnetic scars that rotate endlessly through space. In reflection, rotating spotted stars illustrate a subtle form of variability. They do not explode or collapse, nor do they pulse in grand cycles. Instead, they show their rotation through small changes, the play of light and shadow, as magnetic spots drift into view. Their light curves are modest, but they reveal rotation activity and age-linking surface patterns to deep dynamo processes. By following these small modulations, astronomers gain steady insights into how stars' spins slow down and age all through the quiet rhythm of rotation. Another major family of variable stars arises not from pulsation or rotation, but from geometry. These are the eclipsing binary systems in which two stars orbit each other in such a way that from Earth's viewpoint one periodically passes in front of the other. When this happens, the combined light dips, then recovers as the stars move on in their orbits. The result is a repeating pattern of brightness changes that directly reflects the orbital motion. Eclipsing binaries are among the most informative variables because their light curves combined with spectroscopic data allow astronomers to determine fundamental stellar properties with high accuracy. The basic principle is straightforward. In a binary system where the orbital plane is aligned close to our line of sight, one star will occasionally block the other. When the brighter star is eclipsed, the total light falls by a larger amount, producing what is called the primary eclipse, When the fainter star is hidden, the drop is smaller, called the secondary eclipse. Between eclipses, the light remains fairly constant, though it may vary slightly due to the star's shapes or reflection effects. The spacing between eclipses gives the orbital period, which can range from hours to years depending on the system. The depth of the eclipses provides information about the relative brightness of the two stars. A deep primary eclipse means the brighter star is being hidden, while the depth of the secondary eclipse reveals how much light comes from the fainter star. The duration of the eclipse indicates the sizes of the stars relative to the orbit, and the shape of the ingress and egress curves reveals whether the stars have sharp or diffuse edges. Together, these features allow astronomers to model the system in detail. Eclipsing binaries are classified into categories based on how closely the stars interact. Detached binaries are those where each star is well within its Roche lobe, the region where its gravity dominates. They orbit without exchanging significant matter. Semi-detached binaries are those where one star fills its Roche lobe and transfers mass to the other, often forming an accretion disk. Contact binaries are so close that both stars fill their lobes and share a common envelope, exchanging material directly. Each type produces distinct light curves and reflects a different stage of binary evolution. The classic example of an eclipsing binary is Algol in the constellation Perseus. Its name means the demon star, reflecting the way it appears to fade and recover every few days. Algol consists of a hot, bright main sequence star and a cooler, fainter companion that periodically passes in front. The regularity of Algol's dimming has been known since antiquity, though its explanation as an eclipsing binary came much later. Algol systems are now recognized as common, and their study has contributed greatly to our knowledge of stellar masses and radii. Spectroscopy adds a crucial dimension. As the stars orbit, their spectral lines shift due to the Doppler effect. Measuring these shifts reveals their velocities. Combining velocity curves with light curves allows the determination of stellar masses, radii, and densities. Few other methods provide such direct and precise measurements. Eclipsing binaries are therefore fundamental calibrators in stellar astrophysics. They provide the benchmarks against which models of stellar structure and evolution are tested. In some cases, eclipsing binaries also show pulsations or spots complicating the light curves. These combinations are valuable as they allow simultaneous study of multiple physical processes. For example, stars in eclipsing binaries that also pulsate provide direct measurements of both orbital parameters and internal structure. Similarly, stars with spots can reveal surface activity alongside orbital motion. Untangling these effects requires careful modeling, but the reward is a deeper understanding of stellar behavior. Eclipsing binaries also serve as distance indicators, though in a different way than Cepheids or RR Lyrae. By measuring stellar radii and luminosities directly, astronomers can calculate absolute magnitudes. Comparing these with apparent magnitudes gives distances. This method has been used to measure distances to nearby galaxies, complementing other approaches. While it is more observationally demanding, it provides independent checks that are important for the cosmic distance scale. The frequency of eclipsing binaries discovered has grown rapidly thanks to large surveys. Automated telescopes and space missions have monitored millions of stars, revealing thousands of new systems. Some show unusual features such as eccentric orbits producing unequal eclipse spacing or additional companions causing variations in eclipse timing. These variations can reveal the presence of third stars or even planets in the system. Thus, eclipsing binaries are not only laboratories for stellar physics, but also detectors of companions otherwise unseen. Contact binaries present especially interesting cases. In these, the stars orbit so closely that they share a common outer layer. Their light curves show continuous variation, with the stars appearing brighter when seen side by side and fainter when eclipsed. The two stars often equalize in temperature despite differences in mass due to energy exchange through the shared envelope. These systems challenge models of stability as mass transfer and angular momentum loss can drive them toward merger. Studying their light curves provides clues about the processes leading to coalescence and the possible formation of unusual objects. Semi-detached binaries with mass transfer from one star to another link eclipsing binaries to cataclysmic variables. The presence of accretion disks, hotspots, and outbursts adds complexity to the light curves. These systems show that variability due to eclipses can be intertwined with variability due to accretion. Each dip and rise in brightness becomes part of a layered narrative involving orbital motion, mass transfer, and energy release. Their study requires not only photometry, but also spectroscopy and sometimes X-ray observations, since the accreting material can produce high-energy emissions. In reflection, eclipsing binaries show how simple geometry can create profound scientific opportunities. The periodic hiding of one star by another produces light curves that are straightforward to interpret, yet the data extracted are among the most fundamental in astrophysics. The cycles are calm and predictable, repeating endlessly with orbital precision. To watch an eclipse is to witness orbital mechanics written in light a star dimming, not because it has changed, but because another star has quietly passed in front. In this steady alternation, astronomers find the means to weigh stars, measure their sizes, and test the very foundations of stellar theory. Some of the most dramatic forms of stellar variability arise in cataclysmic variables, binary systems where one star is a white dwarf and the other is a normal star that transfers mass to it. The white dwarf is a dense remnant of a star like the Sun, composed mainly of carbon and oxygen, and supported by electron degeneracy pressure. Its companion may be a main sequence star or a slightly evolved star. When the two orbit closely, gravity from the white dwarf pulls gas from the companion. This material flows through the inner Lagrange point, forming a stream that spirals toward the white dwarf. Because of angular momentum, the gas does not fall directly, but forms a disk of hot matter around the white dwarf called an accretion disk. The interaction between the accretion disk, the white dwarf, and the donor star produces sudden and sometimes explosive variability. The defining feature of cataclysmic variables is the occurrence of outbursts. In dwarf novae, the disk remains stable for long periods, then suddenly brightens by several magnitudes before returning to quiescence. These eruptions repeat irregularly, with intervals ranging from days to years. The cause lies in instabilities in the accretion disk. Gas accumulates until density and temperature reach a threshold, triggering a change in viscosity that causes material to rush inward. The sudden release of gravitational energy produces the observed brightening. When the disk empties, the cycle begins again. These outbursts are not explosions of the white dwarf itself, but are dramatic changes in the accretion flow. In classical novae, the variability is even more extreme. Here, hydrogen-rich gas transferred from the companion accumulates on the surface of the white dwarf. As more material piles up, pressure and temperature at the base of the layer increase until hydrogen ignites in a thermonuclear runaway. This burning releases enormous energy, blowing the accumulated shell off into space and brightening the star by 10,000 times or more. The star then gradually fades over weeks or months. Unlike dwarf novae, classical novae involve nuclear reactions, not just changes in the disk. Yet the underlying requirement is the same mass transfer onto a compact white dwarf. Supernovae of type Ia represent an even more dramatic outcome of mass transfer onto a white dwarf, though they are distinct from classical novae. If the white dwarf accretes enough material to approach the Chandrasekhar limit of about 1.5 solar masses, electron degeneracy pressure can no longer support it, and carbon fusion ignites uncontrollably. The entire star is disrupted in a thermonuclear explosion that outshines a galaxy. This is the end state of some cataclysmic variables, though not all reach it. Type Ia supernovae are crucial in cosmology, but they are not periodic variables. They are single catastrophic events that mark the end of the system. The light curves of cataclysmic variables reflect these processes. Dwarf novae show sudden rises of several magnitudes, followed by gradual declines repeating at irregular intervals. Novae show even more dramatic increases with light curves that rise sharply to maximum and then decline with a characteristic shape. Observers classify novae as fast or slow depending on how quickly they fade. These curves carry information about the energy released, the mass of the white dwarf, and the details of the accretion. Careful monitoring of such events allows astronomers to study both accretion physics and nuclear burning under extreme conditions. Spectroscopy of cataclysmic variables reveals emission lines from the accretion disk signatures of hot gas spiraling around the white dwarf. During outbursts, these lines change in strength and shape, tracing the dynamics of the disk. In novae, spectra show lines from newly ejected material often enriched with elements created in nuclear reactions. These observations confirm that novae contribute to the chemical enrichment of the galaxy by dispersing carbon, nitrogen, oxygen, and other elements. Thus, cataclysmic variables play a role in galactic ecology, returning processed material to the interstellar medium. Cataclysmic variables are diverse. Some systems are magnetic with white dwarfs, whose strong fields channel accretion flows directly onto their poles. These are called polars or intermediate polars. Their light curves show not only outbursts, but also modulations linked to the rotation of the white dwarf. Others show super outbursts, brighter and longer-lasting eruptions thought to involve tidal interactions in the disk. Still others show quasi-periodic oscillations, rapid flickers of light caused by instabilities in the innermost disk regions. Each subtype adds detail to the broad picture of how matter behaves in strong gravity. The study of cataclysmic variables requires continuous monitoring since outbursts can occur unpredictably. Amateur astronomers contribute significantly by watching known systems and reporting brightenings. Professional observatories, both on the ground and in space, then follow up with detailed measurements. The American Association of Variable Star Observers maintains extensive databases of such observations, providing long-term records that are invaluable for understanding cycles and trends. These partnerships illustrate how variable star astronomy bridges professional and amateur efforts. Cataclysmic variables also connect to the larger field of binary evolution. Mass transfer alters both stars. The donor star loses mass, changing its structure and orbit. The white dwarf gains mass and angular momentum, approaching critical limits. Over time, the system can evolve through different stages from detached to semi-detached to contact or toward merger. Studying these systems informs theories of binary dynamics, accretion physics, and explosive transients. They are laboratories for extreme astrophysics where dense matter, strong gravity, and nuclear reactions combine. In reflection, cataclysmic variables remind us that variability is not always gentle or regular. In these systems, quiet accumulation gives way to sudden release, producing light curves with sharp spikes and deep lessons about energy and instability. The stars themselves are not destroyed by dwarf or classical nova outbursts, but they are changed, their surroundings enriched and their stories advanced. To watch such a star is to witness cycles of build-up and eruption, patient preparation, followed by brief brilliant display. In these cycles, astronomers find clues about accretion, nuclear physics, and the fates of close binaries. The rhythms are irregular, but the science is steady, showing how even violent variability can illuminate the quiet structure of the universe. Among variable stars, there exists another class that shows sudden sharp changes in brightness, caused not by pulsation rotation, or eclipses, but by magnetic activity. These are flare stars, also known as UV-Ceti-type stars. They are usually small, cool red dwarfs with masses less than half that of the Sun, but their magnetic fields are intense and their atmospheres turbulent. From time to time, they produce outbursts in which the brightness increases dramatically in minutes, sometimes by factors of several, before fading back to normal. The phenomenon is similar to solar flares on the Sun, yet on flare stars, the events are often much stronger relative to the star's overall output. The cause of flares lies in the twisting and reconnection of magnetic field lines. In stars with convective outer layers, motions of plasma generate magnetic fields through a dynamo process. These fields can become tangled and store energy. When they reconnect, energy is released suddenly in the form of radiation heating and particle acceleration. On Earth's Sun, such events produce bursts of X-rays, radio waves, and visible light. On flare stars, the same process occurs, but often with far greater relative intensity, because their rapid rotation and deep convection zones amplify magnetic activity. Light curves of flare stars are distinctive. A flare begins with a rapid rise in brightness, often within seconds or minutes, followed by a slower decline lasting from minutes to hours. The amplitude can be small or large depending on the energy released. Some flares increase brightness by a few tenths of a magnitude, while the most extreme can brighten the star by factors of several. Because they are unpredictable, light curves of flare stars are usually flat and steady until suddenly interrupted by sharp spikes. Continuous monitoring is required to capture these events in detail. Spectroscopy during flares reveals emission lines from heated plasma, especially the hydrogen-Balmer series. X-ray and ultraviolet observations show that high-energy radiation is also produced. These data confirm that flares heat the star's outer atmosphere to millions of degrees and accelerate charged particles. The process is violent at the local level, but the star as a whole survives without lasting damage. Instead, the flares represent surface manifestations of the star's magnetic activity, repeating over and over across timescales of hours to days. Flare stars are common because most stars in the galaxy are red dwarfs. These small stars make up the majority of stellar populations, and many are magnetically active, especially when young. Surveys show that a significant fraction of nearby red dwarfs exhibit flares detectable from Earth. Because they are faint in quiescence, their sudden brightenings can stand out. Amateur astronomers with modest equipment can sometimes detect flares, while professional observatories study them with sensitive instruments across multiple wavelengths. The frequency and intensity of flares vary with age and rotation. Young red dwarfs rotate quickly, driving strong dynamos and frequent flares. As they age, they lose angular momentum, their rotation slows, and their magnetic activity declines. Thus, the presence of strong flares is a marker of youth. In this sense, flare activity provides information about stellar evolution. However, some red dwarfs remain active for billions of years, showing that magnetic phenomena can persist long after stars leave their earlier stages. The implications of flares extend beyond stellar physics. Many red dwarfs host planetary systems, and their habitable zones lie close to the star because of the star's low luminosities. This means that planets in these zones are exposed to frequent and intense flares. Ultraviolet and X-ray radiation from such flares could strip atmospheres or affect surface conditions, influencing the habitability of these worlds. Studies of flare stars therefore connect to the broader field of exoplanet science, raising questions about whether life could endure around active red dwarfs. Not all flare stars are red dwarfs. Some larger stars also show flare-like activity, though on different scales. The Sun itself is technically a flare star, though its flares are modest compared to those of active red dwarfs. Still, the Sun provides a close example, allowing detailed study of magnetic reconnection and plasma behavior. Lessons from solar flares apply directly to understanding flare stars, though the magnitudes differ. Conversely, studying extreme flare stars helps place the Sun's activity in a galactic context, showing that it is relatively quiet compared to many of its smaller neighbours. The unpredictability of flares poses challenges. Unlike Cepheids or eclipsing binaries whose variations follow precise cycles, flare stars erupt without regularity. This makes them difficult to model and requires statistical approaches. Observers monitor large numbers of stars to estimate flare rates and energies. Space telescopes that observe continuously provide especially valuable datasets capturing hundreds of flares across thousands of stars. These surveys build a statistical picture of magnetic activity in the galaxy. The result is an understanding not of individual cycles, but of overall patterns of stellar magnetism. The energy released in flares is immense. A single flare on a red dwarf can equal the total energy output of the star in several hours or even days. Some so-called superflares have been recorded with energies hundreds of times greater than the larger solar flares. These extreme events highlight the power stored in stellar magnetic fields and the efficiency of reconnection in releasing it. While dramatic, these events are still natural processes that occur without destroying the star. They are part of the normal life of magnetically active stars. In reflection, flare stars illustrate the restless nature of magnetic fields in stellar atmospheres. Unlike the steady breathing of pulsators or the predictable dips of eclipsing binaries, flare stars shine quietly until suddenly, without warning, they blaze with energy. Their light curves are punctuated by spikes, brief bursts against a background of constancy. For astronomers, these flares are signals of magnetic strength, convection, and rotation. For planets orbiting close by, they may be decisive in shaping environments. In every case, the flare is a reminder that even the smallest stars can reveal themselves in brilliant if fleeting flashes of light. Clusters of stars provide a natural laboratory for the study of variable stars. Because the stars in a cluster form at roughly the same time from the same molecular cloud, they share age and chemical composition, though they differ in mass. This shared background allows astronomers to compare stars under controlled conditions, isolating the effects of mass and evolution. When variable stars are found in clusters, their behavior can be linked directly to the properties of the cluster as a whole. This makes clusters invaluable for testing theories of stellar variability structure and evolution. Globular clusters, which are dense spherical collections of hundreds of thousands of old stars, are particularly rich in variable stars. RR Lyrae stars are common within them, lining up along the instability strip on the Hertzsprung-Russell diagram. Because RR Lyrae stars have nearly uniform luminosities, they provide standard candles for measuring distances to globular clusters. By establishing distances, astronomers determine the sizes and spatial distribution of these ancient systems. The ages of globular clusters among the oldest objects in the galaxy are constrained by the positions of RR Lyrae stars and other variables within their diagrams. Thus, variable stars in globular clusters tie together cosmological timescales with the physics of pulsation. Open clusters, which are looser groups of younger stars, also contain variable stars, though of different types. Delta Scuti stars are often found in these clusters, occupying the instability strip at lower luminosities. By analyzing their pulsations, astronomers probe the internal structures of intermediate mass stars. Cepheids, being more massive and luminous, are rare in most open clusters, but can be found in some of the youngest and richest ones. When a Cepheid is clearly a member of an open cluster, its distance can be measured independently by cluster methods, providing an anchor for the period-luminosity relation. This combination strengthens the use of Cepheids as distance indicators beyond the Milky Way. Variable stars in clusters provide insight into metallicity effects. The chemical composition of a star affects its opacity, which in turn influences pulsation. Clusters with different metallicities therefore show variables with different periods and amplitudes. Comparing RR Lyrae populations in metal-poor and metal-rich globular clusters reveals systematic shifts in their properties. These differences are important when using RR Lyrae stars to measure distances, since calibrations must take metallicity into account. Thus, clusters offer a natural way to study how composition alters variability. Light curves of cluster variables also provide information about cluster dynamics. In dense globular clusters, close encounters between stars can form binary systems leading to eclipsing binaries, or cataclysmic variables. These objects serve as traces of dynamical interactions in crowded stellar environments. Observing them provides evidence of how stars exchange energy and mass in clusters over billions of years. In open clusters where interactions are less common, eclipsing binaries reveal more about normal binary evolution rather than dynamical effects. In both settings, variability points to the role of binaries in shaping cluster populations. Modern surveys have expanded knowledge of cluster variables dramatically. Space missions and wide-field ground-based programs have detected thousands of variables in clusters, many with subtle variations that earlier observers could not detect. In globular clusters, the full population of RR Lyrae stars can now be catalogued with high precision, refining the distance scale. In open clusters, continuous monitoring reveals not only pulsators, but also rotational variables with star spots. These datasets show that variability is not confined to a few spectacular cases, but is widespread across cluster populations. Studying variable stars in clusters also helps calibrate evolutionary models. The position of a variable in the cluster's Hertzsprung-Russell diagram can be compared with theoretical tracks of stellar evolution. The observed periods and amplitudes then test predictions of pulsation models. This cross-check between evolution and variability strengthens both fields. For instance, if models predict that stars of a certain mass and age should pulsate in a given way, but the cluster variables show something different, the models must be revised. Clusters thus provide benchmarks that guide theoretical improvements. Cepheids in clusters have been especially important. Because cluster distances can be established independently, Cepheids in clusters offer absolute calibrations of the period-luminosity relation. Early in the 20th century, this connection helped establish the scale of the Milky Way. Today, with precise parallaxes from Gaia cluster Cepheids, remain important for cross-checks and for tracing spiral structure. Their light curves, when placed in the context of cluster diagrams, confirm how massive stars evolve through the instability strip. The combination of pulsation data and cluster membership grounds Cepheids firmly in stellar evolution theory. In globular clusters, RR Lyrae stars provide another key benchmark. Their uniform brightness allows determination of cluster distances, while their abundance provides statistical power. By measuring periods, amplitudes, and light curve shapes across clusters, astronomers refine the calibration of RR Lyrae as distance indicators. They also discover patterns such as the Oosterhoff dichotomy, in which globular clusters fall into two groups with different average RR Lyrae periods. This dichotomy is linked to metallicity and evolutionary differences, and studying it deepens understanding of both variable star physics and cluster properties. Eclipsing binaries and clusters also have a special role. By modelling their light and velocity curves, astronomers can determine precise masses and radii of stars. When such binaries are confirmed as cluster members, their properties give direct tests of stellar models at the cluster's age and composition. This has been done in both open and globular clusters, providing critical checks on theoretical predictions. Because clusters provide a uniform environment, the results are particularly robust. Eclipsing binaries in clusters therefore complement pulsating variables, offering another path to fundamental parameters. The presence of cataclysmic variables in globular clusters adds another layer. These systems often form through dynamical encounters in dense cores. Their numbers and properties inform models of cluster dynamics and binary interactions. Monitoring them over time shows how close binaries evolve in environments where encounters are frequent. They highlight the role of variability not just in individual stellar evolution, but also in the collective life of dense stellar systems. In reflection, clusters reveal the collective aspect of variability. While variable stars can be studied individually, their meaning deepens when seen in the context of a population that shares age and composition. In clusters, variables line up along predictable paths, confirming theories and revealing exceptions. They act as signposts of evolution, marking key transitions across the Hertzsprung-Russell diagram. Observers trace their light curves patiently, cycle after cycle, knowing that within these variations lie answers to questions about distance, age, composition, and dynamics. The stars change individually, but together they form patterns that map the structure and history of the galaxy. One of the most important applications of variable stars is their role in measuring cosmic distances. Because stars are too far away to measure directly in most cases, astronomers rely on indirect methods. Variable stars provide some of the best tools for this work because their properties connect observable quantities such as period or light curve shape with intrinsic luminosity. By comparing intrinsic brightness with observed brightness, distances can be calculated. This method is central to building the cosmic distance ladder, the step-by-step framework that extends measurement from the solar neighborhood to the farthest galaxies. Cepheid variables are the classic example. Their period-luminosity relation allows astronomers to determine luminosity simply by measuring the period of their pulsations. Once luminosity is known, it can be compared with apparent brightness to find distance. Because Cepheids are luminous, they can be seen across millions of light-years, making them essential for measuring distances to nearby galaxies. This was how Edwin Hubble discovered that the Andromeda Nebula was not a gas cloud within the Milky Way, but a separate galaxy far beyond. That realization, built on Cepheid variables, transformed our understanding of the universe. RR Lyrae stars play a similar role on smaller scales. Their nearly uniform absolute magnitudes make them standard candles within the Milky Way and nearby galaxies. They are not as bright as Cepheids, but they are abundant in globular clusters and galactic halos. Measuring their apparent brightness gives the distance to their host clusters or galaxies. In this way, RR Lyrae stars have been used to map the structure of the Milky Way, tracing the extent of its halo and the distribution of ancient stellar populations. They provide a foundation for understanding galactic structure. Mira variables and other long-period pulsators also contribute, though with less precision. They follow period luminosity relations, particularly in the infrared, where their variability is smoother and less affected by dust. This makes them useful for measuring distances to galaxies with ongoing star formation, where red giants are common. Their advantage lies in their infrared brightness, which penetrates interstellar dust. Although less precise than Cepheids, they extend the reach of variable stars into regions where dust obscuration is strong. Eclipsing binaries provide another method. By analyzing their light curves and velocity curves, astronomers determine the radii and luminosities of the stars. From this, absolute magnitudes are derived and distances can be calculated. This method does not depend on empirical relations but on direct physical modeling. When eclipsing binaries are found in other galaxies, they provide independent distance measures. For example, distances to the Large and Small Magellanic Clouds have been measured precisely using eclipsing binaries confirming results from Cepheids and other indicators. The cosmic distance ladder depends on calibration. Nearby Cepheids and RR Lyrae must have their distances measured by parallax to establish the 0 point of their relations. Space missions such as Hipparcos and Gaia have provided accurate parallaxes for many variable stars anchoring the ladder securely. Once the 0 point is fixed, the relations can be applied to more distant stars. This chain of calibration extends from parallax to Cepheids, from Cepheids to galaxies, and from galaxies to supernovae and beyond. Variable stars occupy the crucial middle rungs of this ladder. The accuracy of distance measurements depends on understanding the details of variable star behavior. For Cepheids, metallicity affects the period luminosity relation, shifting luminosity slightly. Interstellar dust dims and reddens light, altering apparent brightness. Careful corrections must be applied to ensure accuracy. Observing in multiple wavelengths, especially infrared, helps reduce uncertainties. For RR Lyrae stars, calibration requires accounting for metallicity as well, since their absolute magnitudes vary with chemical composition. Continuous refinement of these relations ensures that variable stars remain reliable distance indicators. Variable stars also help trace the three-dimensional structure of galaxies. By measuring distances to Cepheids in different regions of a galaxy, astronomers map its spiral arms and thickness. In the Milky Way, Cepheids outline the spiral structure while RR Lyrae trace the halo. In the Magellanic Clouds, Cepheids reveal the depth and orientation of the galaxies. These applications show that variable stars are not only tools for distance, but also for structure mapping the shapes and distributions of stellar systems. The importance of Cepheids extends even further to cosmology. Distances to galaxies measured by Cepheids calibrate the luminosities of type Ia supernovae. These supernovae, being much brighter, can be seen at cosmological distances. By anchoring their luminosities with Cepheids, astronomers extend the distance scale to billions of light-years. This connection was central to the discovery that the expansion of the universe is accelerating, leading to the concept of dark energy. Thus, the humble light curves of Cepheid variables are linked directly to some of the most profound discoveries in modern cosmology. Eclipsing binaries complement this picture by providing independent checks. Their distances are determined without reliance on empirical relations, reducing systematic uncertainties. By comparing distances from eclipsing binaries with those from Cepheids and RR Lyrae, astronomers verify the consistency of the ladder. Agreement among different methods strengthens confidence, while discrepancies highlight areas needing refinement. Such cross-checks are essential when measurements are used to determine fundamental constants, such as the Hubble constant, which describes the rate of cosmic expansion. Long-term monitoring of variable stars ensures that distance indicators remain accurate. Period changes in Cepheids caused by stellar evolution can shift their place in the period luminosity relation. Tracking these changes refines calibrations. New types of variables may also emerge as potential distance indicators, such as certain types of red giants or other pulsators. Each addition or refinement strengthens the ladder and expands its reach. The continuing study of variable stars therefore underpins the accuracy of all distance scales in astronomy. In reflection, variable stars provide quiet but powerful tools for measuring the cosmos. Their light curves are not only records of stellar physics, but also keys to distance. Cepheids, R, Lyrae, and eclipsing binaries all contribute each on a different scale. Together they form overlapping, reinforcing steps that carry measurement outward from the solar neighborhood to the most distant galaxies. Their cycles of brightness, observed patiently and interpreted carefully, make the vastness of space measurable. The stars change gently and predictably, and in those changes lies the means to chart the universe itself. Even though variable stars have been studied for centuries, many uncertainties remain. Their diversity is so great that classification systems often struggle to capture all possibilities. Some stars fit neatly into categories such as Cepheids, irregular or eclipsing binaries, but others show properties of more than one class or defy classification altogether. This complexity reflects the many different physical processes that can cause variability, as well as the ways in which those processes interact. Pulsation, rotation, eclipses, accretion, and magnetic activity can combine in a single system, producing light curves that are intricate and difficult to interpret. Astronomers refine classification systems continually, but edges remain blurred, and new observations frequently reveal exceptions. One area of uncertainty lies in the detailed physics of pulsation. The Kappa mechanism explains much of what is seen in Cepheids, RR Lyrae and Delta Scuti stars, but not all observed features match theory. For example, the Blaschko effect in RR Lyrae stars, where amplitude and phase modulate over longer timescales, remains poorly understood. Proposed explanations include resonances between pulsation modes, interactions with magnetic fields or convective cycles, but no consensus has been reached. Similarly, non-radial pulsations observed in many stars reveal more frequencies than models predict, pointing to missing physics in opacity, convection, or rotation. These mismatches highlight how stars continue to surprise even in well-studied domains. Metallicity is another source of uncertainty. The abundance of elements heavier than helium affects opacity, and therefore pulsation, shifting the boundaries of the instability strip and altering period luminosity relations. Observations show that Cepheids in metal-poor galaxies have slightly different properties from those in metal-rich environments. Calibrating these effects is essential for using Cepheids as precise distance indicators, since even small differences can affect measurements across millions of light-years. While progress has been made, questions remain about the full impact of metallicity on variability. Binary interactions complicate matters further. Many stars exist in binary or multiple systems, and their evolution is shaped by mass transfer, tidal forces, and orbital changes. When variability arises in such systems, it may be difficult to separate intrinsic pulsations from extrinsic effects. Semi-detached and contact binaries can display light curves influenced by eclipses, accretion disks, and spots all at once. Cataclysmic variables with their outbursts and novae represent extremes of binary interaction, but even more ordinary binaries can show unexpected forms of variability. Modeling these systems requires integrating multiple physical processes, each with uncertainties. Magnetic activity also poses challenges. Starspots and flares are common, but their behavior is irregular and difficult to predict. Light curves modulated by rotation may drift as spots grow, shrink, or migrate across latitudes. Flares occur without warning, adding noise to otherwise steady curves. While statistical studies reveal general patterns, the specifics of magnetic cycles and dynamo processes remain uncertain. The Sun provides a detailed example, but even there, many questions about solar cycles and flare prediction remain unanswered. Extrapolating to other stars adds further complexity. Observational limits contribute to uncertainty as well. Ground-based telescopes cannot observe continuously due to day-night cycles, weather, and atmospheric interference. This introduces gaps and noise in light curves. Space missions such as Kepler and TESS have improved matters, providing continuous high-precision monitoring, but their durations and fields of view are still finite. Some variables have periods longer than the lifetimes of such missions, requiring decades or centuries of data to understand fully. Long-term monitoring by networks of amateur and professional astronomers fills this gap, but coordination and consistency are always issues. Another area of ongoing debate concerns the calibration of distance indicators. Cepheids and RR Lyrae stars form the foundation of the cosmic distance ladder, but differences in calibration methods have led to tensions in cosmology. The Hubble constant, which measures the rate of cosmic expansion, differs depending on whether it is derived from Cepheid-calibrated supernovae or from cosmic microwave background data. This tension may signal new physics, but it could also reflect lingering uncertainties in variable star calibration. Refining period luminosity relations correcting for metallicity and dust, and cross-checking with eclipsing binaries remain active areas of research. In addition, variable stars challenge models of late stellar evolution. Long-period pulsators such as mirror variables and semi-regular variables lose mass through pulsation-driven winds, but the details of how pulsation couples with dust formation and radiation pressure are not fully understood. Models struggle to reproduce observed amplitudes and irregularities. Yet these processes are crucial for understanding how stars enrich the interstellar medium with carbon and heavier elements. Without precise knowledge of variability in late stages, predictions of galactic chemical evolution remain uncertain. Even classification itself remains unsettled. Organizations that catalogue variable stars maintain extensive lists, but new discoveries blur boundaries. Space-based surveys reveal variables with mixed or unusual properties, such as stars that pulsate in unexpected modes or binaries with atypical light curves. Some stars appear stable from the ground but show subtle oscillations in space data. Others show variability only intermittently. These findings suggest that the spectrum of variability is broader than current systems capture. Classification will likely evolve toward describing physical mechanisms rather than fitting stars into rigid categories. Despite these uncertainties, progress continues steadily. Improved models of opacities and convection are closing gaps in pulsation theory. Infrared observations are refining period luminosity relations by reducing dust effects. Long-term monitoring is revealing slow period changes that match evolutionary predictions. Statistical analyses of flare rates and rotational modulations are mapping magnetic activity across stellar populations. Each uncertainty becomes an opportunity for refinement, and each unresolved question drives further observation and theory. In reflection, the uncertainties of variable star research remind us that variability itself is a signal of complexity. Stars that change brightness are revealing processes that static stars keep hidden. The irregularities, deviations, and exceptions are not obstacles but clues. They show that stars are dynamic systems influenced by composition, environment, companions, and magnetic fields. By following these quiet irregularities with patience, astronomers deepen their understanding of stellar physics and cosmology. The questions remain open, but the answers lie encoded in the calm rise and fall of starlight waiting to be traced and understood. Variable stars taken together reveal a broad picture of how stars live, change, and interact. They are not a separate class of objects, but normal stars caught in moments when their light does not remain steady. Some pulsate because their outer layers trap and release energy, their envelopes breathing in and out like vast spheres of gas responding to shifts in opacity. Some rotate with surfaces scarred by magnetic fields, their spots passing quietly across the line of sight. Some belong to pairs orbiting companions that eclipse one another with rhythmic precision. Others exist in extreme binaries where mass flows and accumulates until sudden eruptions transform their brightness. Each type of variability points to a different piece of stellar physics, and together they form a map of processes that shape the evolution of stars and galaxies. The role of variable stars extends beyond classification. Their cycles and irregularities make it possible to test theories of stellar interiors. Pulsations reveal density and temperature profiles. Non-radial oscillations uncover rotation, and layering deep inside stars. Variability due to rotation traces the strength of magnetic dynamos and the lifetimes of surface features. Eclipsing binaries allow direct measurement of mass and radius, the most fundamental stellar properties. Cataclysmic variables reveal accretion physics, nuclear ignition, and the effects of strong gravity. Flare stars demonstrate the extremes of magnetic reconnection. In every case, the change in brightness is a doorway to hidden processes otherwise unreachable. These stars also link directly to the structure of galaxies. Cepheids trace spiral arms marking sites of recent star formation. Irregular outline the halos and globular clusters that preserve the oldest populations. Mirror variables and other long-period pulsators show where mass loss enriches the interstellar medium with heavy elements. Clusters filled with variables reveal how age and composition affect stellar behavior. Together, these stars serve as tracers, helping to map the three-dimensional structure and history of the Milky Way and its neighbors. Their importance lies not only in their individual behavior, but also in the patterns they form across populations. The cosmic distance scale depends critically on them. Cepheids with their period luminosity relation bridge the gap between parallax measurements in the Milky Way and supernova measurements in distant galaxies. Irregular provide a step for nearby systems, extending the ladder into the halo and local group. Eclipsing binaries confirm distances independently, offering consistency checks that anchor the scale. These stars, steady in their cycles, make the vastness of the universe measurable. Without them, cosmology would lack secure foundations. With them, astronomers have traced the expansion of the universe and uncovered dark energy, all beginning with the gentle pulses of starlight. The study of variability also enriches understanding of stellar lifetimes. Stars evolve through stages in which they pass through the instability strip, becoming pulsators for only a fraction of their existence. Long-period pulsators signal late stages of life-shedding mass and preparing to form planetary nebulae. Cataclysmic variables show how binaries evolve through mass transfer, sometimes ending in explosions that enrich galaxies with heavy elements. Each variable star is a snapshot of an evolutionary process, a clue to where the star has been and where it is going. By cataloguing and analysing them, astronomers piece together the timeline of stellar change. Modern technology has transformed the study of variable stars, but the essential approach remains the same: careful observation over time. Long before electronic detectors, astronomers tracked variables with the naked eye and simple instruments. Today, space observatories record light curves with exquisite precision, revealing subtle variations undetectable from Earth. Large surveys collect data on millions of stars, turning variability from isolated cases into a vast field of statistical study. Yet continuity with the past remains, as amateur observers still contribute visual estimates and small telescope data, extending light curves across decades. The blend of tradition and modernity defines the field. Despite progress, variable stars continue to present mysteries: the Blaschko effect in Irregular, the irregularities in mirror variables, the intricacies of multiple pulsation modes, and the unpredictability of flares all challenge theory. Each unresolved detail is an opportunity to refine physics, whether in opacity, convection, magnetism, or binary dynamics. These uncertainties ensure that variable star research remains active, drawing on new data and new models. The stars themselves provide endless material for study, their variations steady but never fully explained. The scientific role of variable stars is matched by their contemplative aspect. Their light curves unfold with calm repetition, each cycle following the last with measured regularity. To observe them is to follow rhythms on timescales longer than human breath or heartbeat, but no less steady. Cepheids pulse over days, Near us over months, eclipses repeat with orbital precision flares burst and fade within hours. Each timescale is a reminder of the many clocks in the universe running together in silence. Their changes are not chaotic, but ordered, revealing the deep physical structures that govern stars. In reflection, variable stars can be seen as teachers of patience and persistence. They do not reveal their secrets in a single glance, but require long monitoring, careful recording, and thoughtful analysis. They invite observers to return night after night, season after season, building records that extend across lifetimes. In this way, variable stars connect individuals to the slow processes of the cosmos. The data they yield are not only numbers, but stories carried in cycles of light that echo across space and time. The wider role of variability is thus twofold. On one side, variable stars are practical tools measuring distances, tracing structures, and testing theories. On the other, they are quiet examples of change reminders that even stars are not fixed points but evolving systems. They embody the balance between stability and variability that defines the universe at every scale. To study them is to learn both the measurable facts of astrophysics and the contemplative truth that change even in the heavens is natural and revealing. In their steady alterations, variable stars illuminate not only the physics of the cosmos, but also the quiet rhythm of existence itself.